For the assignment number 5, our main objective is to do a pattern identification using radial basis function network along with hierarchical clustering. So in the given problem, we have 7 cards and I have converted them into sequences of ones and zeros. And then I have converted them into this binary 8-bit binary into decimal form and then divided by 255 such that the values lies between 0 and 1. So we have 3%. Suppose the cards of A are C1, C2, and C3. The first three are the cards of A, the next two are the cards of B, and the last two are the cards of C. So possible input card sequences includes such that out of the 3 cards, A can only take 2 cards at a time, B can take 1 card at a time, and C can take 1 card at a time. So we can see what are the different combinations for CA. So after converting into from binary to decimal and then dividing by 255, so we are getting that there are 3 sort of values: 0.6314, 0.4392, and 0.6471. So this could be the possible combination for A1 and A2. These are the cards of A1, A2, again this A1, A2, this A1. There are 3 possible combinations. And for B, similarly for B and C. So for B, we have one at a time, this one also. So 2 distinct values, one at a time. Similarly for C. So now we can here have permutations among the cards, the possible combinations of cards. So we can run a permutation for look for permutations from all the 3 combinations that we have for A, one at a time for B, and one at a time for C. And similarly, we can do this for all the possible combinations of CA, CB, and CC. And we can get a set of possible inputs that we can give, a set of possible pattern inputs. So these are some 288 possible patterns that we can give. And there are some conditions that a valid card sequence would be the one if the first input is A's input, the second card is also of A, and the third card is of either C or either B. So this loop identifies the valid card sequences, that what are the valid cards which will open the vault and what are the invalid cards which will not open the vault. So if we run up till here, we'll see that the valid sequences are 48. So this 48 patterns or the sequences are solely responsible for opening the vault. If other input is given, it will not open the vault. So that invalid sequences are stored in this particular matrix. So now we go into hierarchical clustering. That we have to solve the problem using 4 different Gaussian functions. So for the 4 different Gaussian functions, we are trying to divide it into 4 different clusters. A total set of 288 cross 4 into 4 different clusters. So SCQ1 divides finds the Euclidean distance between the pairs of the patterns. PD function identifies the Euclidean distance between the patterns, and we can visualize this in the square form. So we're using the square form function. Suppose I run here. So this gives us the Euclidean distance between the pairs. And if you want to visualize, we can see it using the square form function also. So yeah, so the distance between the pattern 1 and pattern 2 is 0. Distance between pattern 2 and pattern 1 is 0.2718. Distance between pattern 3 and pattern 1 is 0.1109. So likewise, the distance between every pattern has been stored in this particular matrix. So now we use this distance information and simultaneously views the linkage function which uses this distance information and which can divide or group the objects into a binary hierarchical cluster tree. So this linkage function link pairs of patterns that are in close proximity or are in close neighborhood. And as the patterns are paired into binary clusters, newly formed clusters are grouped into large clusters. So we can see how the clustering operation is done and using the dendrogram and how it looks. So this dendrogram shows us the hierarchical cluster tree, and these small clusters are initially divided into binary, and then it grows smaller ones into the larger ones, and then we finally get this binary uh, hierarchical cluster tree. So from this dendrogram, we are aiming to divide the data set into four clusters. So max cluster can divide this into four using the cluster function. So these are four different clusters are all the data set points. So if we see in the Z1, so these are the patterns, the values of the patterns P1, P2, P3, P4. These are the cards, and this particular cards are grouped into cluster one. This one's in cluster two. This one the cluster three, and the other ones in the cluster four. So you divided 288 patterns in four clusters. So now we individually divide this into the respective clusters. So the cluster 1 contains 44 patterns, cluster 2 contains 76 patterns or sequences, 92 and likewise. So here we find the centers of each and every cluster. The centers would be the ones above which the basis Gaussian functions will be placed. So we want four Gaussian functions to be used. So we need to have four centers of the four clusters that we have found. So center 1, center 2, center 3, center 4 are the four centers of the respective clusters. So we have the values of the centers here. Now the target. There will be two targets. One's target for opening the world will be 1, and if the target for not opening the world would be 0. We have concatenated the target and made a single array out of it. So this target contains ones for all the 48 initial inputs and zeros for the rest of the inputs or the invalid inputs. So now we are calculating the Gaussian function or the phi matrix. The phi matrix basically is the Gaussian function matrix, and for every input we will be having four different Gaussians: phi 1, phi 2, phi 3, phi 4. So this iterative loop will give me 288 cross 4 dimension of size of matrix of phi. So this phi matrix is basically exponential to the power minus of distance of this x contains the valid sequence and the invalid sequence minus the centers of the clusters that we have found to the power to the power 2 divided by 2 sigma square. So sigma is the width of the Gaussian. So now we have successfully converted from approach from P1, P2, P3, P4 to phi 1, phi 2, phi 3, phi 4. So every pattern input has four different Gaussians. So basically, we have now approached using the four bases like Gaussian functions. We have converted uh, a very tedious problem or a very complex pattern classification problems with the basic principle of Cover's theorem that by applying some non-linearity we can grow from we can go to a higher dimensional space where linearly separation is much more likely, or the chances of linear separation is possible, or chances are very high. So if that is achieved, then we only require a single layer neuron which will have only four weights to be updated. So this W is equal to uh, 5 times Y. Here the phi is not a square metric, so we'll take a pseudo inverse of it to find the W. So W is phi inverse target. This target is the ones that we mentioned over here. So now we get this pseudo inverse is 4 cross 288. The target is 288 cross 1. So we have a W metric of 4 cross 1. So we'll have 4 weights corresponding to 4 Gaussian function outputs, which will be summed together to give an output. So here we have our 4 weights. So in this problem, now we only require single neuron, which will have 4 different weights, and the output is equal to the product of phi or the Gaussian function matrix and the W. So this is 28 cross 4. This is 4 cross 1. Again, this output would be 288 cross 1. And this iterative loop gives me the mean square error over all the points. This y1 is the output minus the target, the square. Likewise, we found the mean square error. So we see that mean square error for our problem is very low, but when we see it in y1, this value does not match our desired output. So the desired target or the desired output is 1111 up till 48 for the 48 valid sequences, and then it should go to 0. So if we modify this output, or we can include some bases that we subtract the values of y1 by some value, and then we apply an activation function such as Hartling on it, we can have a clear visualization that which sequence could open the vault and which sequence will not open the vault. Once again, we'll run the code, and if we see that uh, doing some alteration can be helpful or not. So yeah, so now our y1 output is somewhat similar to our desired output. That for the first 48 sequences, it should open the vault. So it's clearly giving me as a 1 as an output. Somewhere it is giving 0 because we have randomly chosen that basis of minus like 0.2. Up till 48, it should give me 1, but in between, it's giving me 0. And after 48, it should show me 0. So up to some extent, it is performing good. And here also the mean square error is 0.2. So using RBF and 4 Gaussian functions, we can convert a very tedious problem which could be solved using MLP, but we might have been using backpropagation algorithm over there. But here we only required to update 4 weights and use a single layer neuron to approximate the function.